Hi, welcome back to the course on object-oriented systems. During the lunch time, there were a couple of questions and I will try to clarify the questions now. The first question is to deal with the notion of instance of and ISA. The person asked a question, what is the difference between an individual object and a class object? If you look at the way I have described, they all look the same. Why is that you made a distinction between the individual object and the class object? Now, the primary difference between the class object and the individual object is as follows. In the individual object is a unique object where you cannot subclass or make further clones of these individual objects. So, they are an object which have their own unique identity and they exist in the physical world. Class objects are abstract objects. In other words, these have an identity in the physical world, these have an abstraction in the physical, they do not have an identity in the physical world. The class objects are objects which are an abstraction of the individual objects which have a physical identity and cannot be further subclassed or cannot be further individualized as such. So, individual objects are individual unique objects, and that's the difference between the individual object and the class object. Otherwise, the process of inheritance and all the other things are very, very similar to both of them. In fact, they are the same. The second question is in relation to dynamic binding. What really is dynamic binding and why is it that a different word that is different terminology that's used for instead of the things which we see in regular compilers? Well, the difference between static and dynamic binding is in dynamic binding we defer the binding process until runtime. That is, during compile time we don't bind the type to the variable or the method to the message selector. The binding is done during runtime, not at the compile time. If it is done at the compile time, it is static binding. Okay, with that we will go to the next module, which is object oriented database systems. Well, I hear that we have a phone call, and let me take the phone call right now. Go ahead. Okay, I guess we don't have it. We'll wait until the end, or maybe please feel free to call me anytime. This section is more oriented for engineering applications, and first I'll discuss the nature of engineering problem solving. Then I will give you a scenario on how typical problems are solved in a collaborative manner. We will discuss the engineering data requirements, what are the characteristics of object oriented database systems that are useful for engineering data requirements. Then we will compare and discuss the advantages of object oriented database systems over relational database systems for engineering applications. I will give you an architecture of object oriented database systems for engineering, and then finally we will summarize. Okay. The engineering process starts with the market needs, where we go and do a data analysis or the market analysis, and you zero in on a particular product during the conceptualization stage. For example, your TV or maybe your car or some elements in your car. If you want to have an intelligent vehicle system in your car, incorporated in your car, you say, well, there's a market for it. You do R&D. From R&D we do design, and design involves coming up with a set of specifications which could be manufactured, and from manufacturing we go to testing stage. From testing stage we go to marketing, and from marketing we go to maintenance. And this process is some kind of an iterative and a collaborative process. In a traditional product development, the way this is done is as follows. I am taking an example in the architectural engineering construction industry, but this example is the same in most industries. Here the architect first does the design and throws it over the wall to the designer. The designer then does some calculations and throws it over the wall to the fabricator. we have a manager who is overseeing all these people, and then we have a client who is paying for all the work, but the client is kind of confused as such. Now, in this process, if I take the design and manufacturing process as the one which I described before, I am only considering the two stages, that is the design stage and the manufacturing stage. The expenses incurred during the design stage are about 3 to 5% of the cost is incurred during the design stage. However, we make 40 to 60% of the commitments during this stage. In the final production stage, we incur 85% of the cost, but we have only can change about 5% of the variables. So, we have control over 5% of the variables versus a large number of variables here. So, what does this translate to? This translates to the following. If you were to make an error during this design stage, and if that error were to cost you $1,000 to fix during the design stage, the same error would cost you $10 million if you catch it during the production stage. Now, this particular problem is not only for engineering problem solving, but also for software development, as we will see later on. So, how do we go about doing it? One way to do it, which is called the shared view, and we will talk about how to implement this during the application section, is that you have a number of agents working together through the computers, and they access a shared database. So, what are the characteristics of this database? And that is what we will put an emphasis from now onwards. Here we have the human beings talking through the computer through the shared database or the shared workspace, and the human and the computer, I call it as an agent. So, we have several agents who are collaborating through this centralized workspace or the data space. So, if you follow this approach, this is also called concurrent engineering or collaborative engineering. If you follow this approach, then we have several advantages. The advantages are the development time is about 30 to 70% less, the time to market is 20 to 90% less, we have fewer engineering changes, the overall quality is increased, we have return on assets is increased. So, we have a number of advantages, and this was based on an analysis done by the National Institute of Standards and Technology and Institute for Defense Analysis, and a host of other organizations found this out. So, let us see how this one will work. Let us go through a scenario and see how this is done in a typical engineering example, where we have a global shared database, and then we have groups forming here. We have an architect, a structural engineer, a geotechnical engineer, and these three people have their own locally shared database, and once they have agreed on some aspects of the problem, they check in and check out into a globally shared database, and then we have a number of other participants who are accessing this globally shared database, and these participants can have further subgroups in there. So, if you look at engineering in such, we have overall we have a number of people working at one level, and we have another set of people working at another level, and so on and so forth. So, this is the notion of nested transactions which happens in engineering. We will come to that in a minute. So, let us see how this what happens in the subgroup, the architect, structural engineer, and the geotechnical engineer. Let us have a closer look at what the architect is doing here. The architect does the preliminary layout in his or her own personal database, and thus posts it into the shared database. Once the architect posts it into the shared database, the structural engineer is immediately notified that there is something for the structural engineer. So, the structural engineer checks out the house objects, does some preliminary analysis and design, and while the structural engineer is doing this, the architect at the same time is continuing out with the details of his or her layout design. The structural engineer completes the design and posts it into the shared database, and when this happens, immediately the geotechnical engineer is notified that there is something for the for the geotechnical engineer, and the geotechnical engineer checks out the column objects and begins doing the preliminary design and layout. And while this process is going on, by the way, the structural engineer also gets a notification. So as people are putting things into the database, people are being notified simultaneously. So the architect continues this process, and at the same time the structural engineer is being notified, the geotechnical engineering is being notified of any changes. So this process keeps going on. As this is going on, the architect can make a change to the initial specifications, because in the design process specifications always change. So the architect decides that the layout that he or she has done before is not appropriate, or there are some initial changes, and they make the changes and post it back into the database. Now note here, many times we may not want to erase the old version for historical purposes. So we say that this particular design is versionable, and once we say that, a version is created and then it is tagged on to the previous version, and at the same time the structural engineer is notified of the change, and the structural engineer now checks out to see whether the components are in agreement with his previous design or not, and then if there are any changes, the structural engineer makes the changes and goes and posts it back into the particular database. As he is doing that, now the geotechnical engineer gets notification, who then checks out the new data for possible redesign, and this process goes on and on, where the versions are continuously being created. Finally, the design is completed and agreed upon by all members if and only if after everyone agrees that the design is okay, and then they post it back into the central database, or the database that we have seen around in this particular slide here. So once the people agree that once they all agree on the aspects of the design problem, they post it into this local shared database, and from there we post it into the globally shared database. Now this is a very fairly complex process, as we have seen, and what are the data requirements for such engineering problem solving? Well, if you look at it, engineering objects revolve around artifacts, about the notion of an artifact. The TV camera, the TV that you are looking into, the camera that I am looking into, these are all artifacts. So engineering is really artifacts based or object based. Artifacts are objects. In engineering we think about objects all the time. These objects have structure. Your TV screen has a structure, your TV has a behavior, is showing my face in there. So so these objects have both structure and behavior. And in engineering we model at various levels of abstraction, especially when we talk about a building. At one level we talk about just the building as such, and another level we talk about the 2D lateral load resisting system, and another level we talk about a 3D lateral load resisting system, and each one of them have some geometric configuration associated with them. Engineering involves complex data structures, complex relationship between various objects. Like your TV, for example, there is a relationship between the tube there, the cathode ray tube, and the housing. That's the TV, the housing for that particular cathode ray tube. Similarly, there are some printed circuit boards in there, and they have a complex relationship to the cathode ray. So there's a lot of complex relationships between various objects, and these objects are tied fairly in a complex manner, and objects are made of one another. Engineering design, as you have seen, is an iterative and collaborative and incremental process where the design objects evolve through an entire lifespan, going through several stages. The tasks and data are shared among engineers, as we have seen in the previous example. So what are the database requirements for engineering problem solving then? So the database requirements are shown here. First, we need it to support complex information processing. Second, because engineering objects have a inherent behavior and structure, and they are very rich in terms of there is some semantics involved in there, the database system should support this semantic schema design. I am using the word schema here to mean a collection of objects, and the word schema is used in relational databases in a different way. Since the objects are related to one another, their objects have constraints, like we have a constraint that the cathode ray tube should be within the housing. So, this is a physical constraint which is placed. So, this particular constraint has to be satisfied no matter what happens. As in engineering, as in other places, we deal with large volumes of data, like when you do a finite element analysis program or a SPICE program, you deal with massive amounts of data, and that data has to be stored on the hard drive. Engineering is unique in the sense that we deal with a lot of geometric and pictorial data. One of the major differences between engineering and software is that in engineering we deal with physical entities which have a well defined geometry, and it is not so in the software, as we will see in module 3. The database should support data sharing, data versioning, and change notification. Remember, when the architect made a change and posted it onto the database, that change has to be notified both to the structural engineer and the geotechnical engineer. So, the database should support change notification. Let us look at some characteristics of object oriented database systems that help in this process, that are very useful and intuitive for engineering problem solving. Object oriented database systems are based on object oriented programming languages. For example, the object system provides you with various levels of data abstraction. It helps you with complex information modeling. Objects have identity, and we will come to the identity part later on. Encapsulation and data hiding. We can have active intelligent data by encoding behavior in the data model, as we saw in the car example, where we had a diagnosis set of diagnosis rules in the car objects, and they offer the object model offers inheritance. In addition to that, most object oriented programmings allow polymorphism. Although object composition is not a part of regular languages such as C++, we can augment this with having object composition such as the part of link, and we will talk about that later on. Object oriented systems, as we have seen before, help in the process of message passing. They are extensible and help in the process of incremental development. Some languages help in dynamic schema evolution, and finally, object oriented programming languages are computationally complete programming languages, and object databases so have the facility or the advantages of this computationally complete programming languages. However, object oriented database systems extend object oriented programming languages by providing persistence, that is, you can store the objects which are created in memory on a physical disk. We can have versioning capabilities. They allow cooperative transactions. We will see cooperative transactions later on. We do type specific concurrency control, recovery, and consistency. In terms of the technological positioning of object databases versus relational databases, we see that in the past we can divide basically the object databases into the fixed model and the extensive model, and based on the query we have navigational query or we have structured query languages. With network based systems have a fixed model and they are based on the navigational query system. The relational databases have a fixed model, but they have a nice structured query language interface to them. The extensible models, the early object oriented models are extensible in terms of schema evolution or the object evolution. However, they mostly provided navigational facilities, and we are seeing a trend towards object SQL or object oriented standard query language, and so the object oriented systems can be positioned around here. Now I will discuss some of the advantages of object oriented database systems over relational database systems. If you look at the current literature, you can see that the object-oriented that the relational database systems are being used quite a lot in many applications, even in engineering problem solving. However, I will show that object-oriented databases are much better for doing the kinds of problems that I have mentioned before. An object-oriented model is a more realistic data model than the tables. If you are an engineer, you don't talk about tables. This is a table which I am sitting on, which is here, of course, but you don't think about a table in terms of representing the TV monitor which you are looking at. So we think about artifacts. Objects are a more natural thing for us than tables. Object-oriented database systems have object model over them. So they provide a much better and a more powerful data model for doing our complex information processing. These are more extensible and flexible, as we have seen that the object model helps in the process. It's easier to build your schema and dynamically evolve the schema. Some languages like C++ don't allow it that easily, but object-oriented database people have added dynamic schema evolution or dynamic object evolution over C++, so they provide this kind of things. And you end up in a smaller size of schema, a smaller size of objects, because you are using the facilities of inheritance, where you can share code, attributes, that is, you can share both structure and behavior. Most of the object-oriented databases are identity based versus the value based in terms of the relational databases. The relational databases are value based, which expresses relationships between two objects by embedding the same value in two or more related objects. So the user defines some unique keys to distinguish between similar entities, and this often results in a duplication of data. The object-oriented systems, on the other hand, are based on identity. What does an identity-based systems do? We relate two or more objects independently of their embedded values. So these things are independent of the values, whereas this is dependent on the values. Now the identity facilitates the notion of sharing by having references from various points to the same objects rather than keeping copies. We'll talk a little bit about object identity later on. And object-oriented programming languages have computationally programming language as their embedded in them versus the impedance mismatch in relational databases. So what does this mean? In terms of relation, we'll talk about it in a few minutes, but if you look at relational databases, the language that you program in is different than the language which is natural to the relational people, that is SQL. Then in terms of the concurrency control, in object-oriented databases, we can do type-specific concurrency control versus the notion of serializability, which the relational people enforce. Now, I will talk about these things after in a few minutes and show you some examples on how the object-oriented systems do these kinds of things. The object-oriented databases have better data versioning capabilities than the relational database systems. They provide greater flexibility for collaborative engineering activities and cooperative work. So in the future, we can see an emergence of object databases being used for collaborative engineering. In object databases, we have intelligent data versus dumb tables in relational. The relational tables have no notion of behavior. They're really dumb tables sitting there. They're flat files, whereas objects have some structure, objects have some behavior, and you can add intelligence to these objects. The query language in object-oriented systems is much more expressive than the SQL that is generally given with relational databases, and we will see some examples of that. So let's clarify these concepts a little more in the following slides. If you look at the relational databases are value based, where the reference is made by value. We have certain keys, and then we map the various relationships because of the values of these keys. Whereas in object databases, we make reference through object identifiers, which are unique identifiers. Generally, they are known as OIDs. So these object identifiers are value dependent, but of course we can allow sharing because we can have multiple references to the same object. There are several ways that one can generate this object identity, because we said we need some unique object identifiers. One way to do it is to generate the address of the object in the main memory. However, the problem with this process is that once the program dies, that particular address also goes away. So this is not a very useful way of doing it, and it is not generally done in database systems. In database systems such as relational databases, one of the things they do is to use the structured addresses where you have, where associated with this each table we can have the volume, the page number, and the slot number on the appropriate disk space. In object oriented systems, we can have a similar thing where we can attach the structured addresses to objects. I will talk about these examples soon. The other approach is to use something called surrogates. In surrogates, we define the object identifiers are globally generated identifiers which are unique, and they do it using some program which is guaranteed to generate a unique object identifier in some manner. Some object databases use this, but most of the C++ based database systems do not use surrogate IDs. Many of them use structured IDs. Then we have typed surrogates. Some systems such as Orion or Itasca, which is a commercial system, uses this typed surrogate. So in terms of the mapping between the relational database and the object database, if you look at the relational databases, the relational database mapping is done in the following manner. There are three levels here: the conceptual, the logical, and the physical level. Really, we don't like to think in terms of relations most of the time. So Peter Chen came up with this entity relationship model. So we define entities along with relationships between these entities. So this entity relationship model, of course, this model does not have inheritance in there. So it's some kind of still a flat structure, not so flat, but doesn't support inheritance and all these things, and no behavior also is encoded in there. So this is mapped to the logical level, which are the relations, and from there you map it into the disk structures. However, in object databases, there are objects, and objects have relationships, and objects inherit information from other objects, and these are mapped directly onto the disk space. So there's a one-to-one mapping from here to here. Now an example which Tom Atwood gives is the following. Suppose you have a Mercedes-Benz. However, you do not have a garage in which the Mercedes-Benz, however the garage door is very small, so the Mercedes-Benz doesn't go in. What you do then is you get the Mercedes-Benz near the garage, dismantle the Benz, and then take it into the garage, and then you can put it back, piece it back together. And that is how a lot of people do nowadays in terms of mapping from objects to relations to these databases. And the reason they do it is because a lot of people have already invested millions and millions of dollars into relational databases. And when we have invested so much money into relational databases, you don't want to throw away your relational databases. So what do? Well, you follow this approach where at the conceptual level we know that objects are a nice way to do things. So we map that objects into the relations, and from there you can use all the advantages of relational databases. Now this approach is fairly good if you have already invested lots and lots of money, that is, you have millions of garages already built, and maybe the cost of disassembling your Mercedes-Benz is not so much. So in that case, you can do this operation going from objects to relations and relations to data structures. On the other hand, if you are starting from fresh, my idea is to go from objects to from object-oriented languages to object-oriented databases. So we provide a seamless integration. Here is another example of that mapping, which is given by Mary Loomis, where you have the relational databases in form of table, and then your programming language uses this SQL type commands to get the information and puts it into a memory structure, makes some changes, again using some SQL type commands, you put it back in here, and this is called the impedance mismatch. Whereas in the object case, what we do is we directly map from the memory into the object oriented database systems, and we do the operations in the memory, do a one-to-one mapping, and we will come to this particular example in a minute or so. The next example that I would like to talk about in terms of the differences between object oriented databases and relational databases is the query example. In object oriented databases, we have an object model. So the object model for our vehicle case looks something like this, where we have a vehicle here, and then I have not shown the behavior here, I have only shown the structure of the object. Remember, here really we are discussing the relational model and the object model. So let's look at the object model for the vehicle again. So the object model for the vehicle looks something like this, where I have the ID, type, color, drivetrain, and this drivetrain is some kind of a composite object here. So there's a reference to vehicle drivetrain, which consists of an engine and a transmission. So the engine is of the type vehicle engine, drivetrain is of the type vehicle drivetrain, engine is of the type vehicle engine, manufacturer is of the type company, which has a name, location, president, and the president is of the type employee, where you have a social security number, name, age, picture, and we have several methods and constraints that we can invoke on this particular employee. The ESA relationship now I have shown by these thick lines, and the references I have shown by these thin lines here. In traditional relational systems, a relational model, because of normalization, we cannot do that. So we have to take this rich complex structure and then break that down into some flat files. So I have broken the objects into the following flat files: vehicle, company, and employee. And my identifier, the way which I point from vehicle to employee, is through this manufacturer, which is a foreign key to the vehicle, and vehicle ID is the primary key here. So the foreign key is between the manufacturer here and the employee here. So the manufacturer name, the manufacturer here and the employee name have to match. So if you were to make a query then to find out the vehicle, all the vehicles whose color is blue and whose manufacturer's location is Detroit, and whose president's age is less than 50. So you want to get hold of all the vehicles whose color is blue and whose manufacturer is located in Detroit and whose president's age is less than 50. The way you do that in an object oriented model is the following. All the object oriented programming languages do not offer the query support. Object oriented databases augment object oriented languages with the database support. So in this case, we send a message called select to the collection of vehicles with the following argument here, where vehicle.color, see the natural way you are doing it, you are saying vehicle.color equals blue and manufacturer.location equals Detroit and president age is less than 50. So this query is some kind of a navigational query. On the other hand, even for the simple example, in relational database systems, I do it in the following manner: select vehicle.id from these three relations, vehicle, company, and employee. Remember, here there is only one object, one class object here, which is the vehicles, where vehicle.color equals blue, which is similar to that. However, now we have to tie the employee and the vehicle, and so the company and the manufacturer. We do it by vehicle.manufacturer equals company.name. So that's how we do this tying in here. If you go back to the previous slide, here the manufacturer is tied by the name attribute of this company. Similarly, the company's president is tied by this name here. So we are tying the manufacturer with the name here, and we are tying the president with the name around here. And we can have one more attribute around here, and in this attribute we can even say vehicle owner, and the owner can be tied to the name here. So the owner can be tied to the name here, the president is tied to the name, and the manufacturer is tied to the name of the company. Now you can see that this is a pretty complex thing, and we can get a lot of confusion even in a simple 3 tables. We can get it, it's pretty confusing as such. Now then we have company.location equals Detroit, and company.president equals employee.name, and employee.age is less than 50. So this is how we do a relational query, and when we do that, we end up with a lots of selects, join, and project operations. Now I have a feeling that for many of the engineering operations or engineering queries that we are going to do, the object-oriented model is, in a worst case, maybe as bad as a relational model, but on an average case it may be much better in terms of efficiency than the relational model. Again, this is my feeling, and we hope to show that in the future. Next, I will discuss about object-oriented database architecture for engineering problem solving. And this is very similar to some of the architectures which are again found in the relational world, because the object-oriented databases, many of the database systems have been influenced by some of the work which is done in the relational database world. And these are the architecture that you find most of the time is the client-server architecture. In the client-server architecture, we have clients here which communicate through a centralized server. There are 4 basic components that are generally available in all object-oriented databases. One is the object manipulation capability. Generally this is part of the programming language with some augmentation. It's a query module, a storage module, and a transaction module. In some systems, the storage module and the transaction module are at the server level, and in some systems such as the Itasca or the Orion, these modules are both at the client level and at the server level. In some object-oriented database systems, we can do object or schema evolution at the server level. In many systems which are based on C++, you cannot do that, and we'll see why not, and we do that at the client level. Similarly, querying, we cannot do it at the server level in many systems, we do it at the client level. So there are different variations of this architecture. What I'm going to do now is to take a couple of these things and give you some examples of the transaction system and the storage system. Let's look at the transaction system. As we have seen, multiple engineers can access the same objects in the database. Now one of the major differences between the financial systems and the object-oriented and the engineering systems is the following. In financial transactions, we enforce the ACID notion, that is, the transactions are atomic, consistent, isolated, and durable. Now to do so, they enforce what is known as serializability by something called a 2-phase commit protocol. So if you use the 2-phase commit protocol, you can enforce serializability. However, serializability has certain problems for the group transactions as such. The major problem with serializability is it is too restrictive, as we will soon see in an example. So the transaction framework for engineering then should support collaborative transactions if you are talking about collaborative engineering. So these are some of the features that we require for engineering, and some of the object-oriented database systems support a few of them. Some of them don't support any of this, and we will talk about that later on when we compare object-oriented databases in module 4. One of the most important things here is that we have to define transactions dynamically during runtime, so that we don't know previously what kind of transactions the engineers are going to do. So these have to be defined at runtime, and the transactions are nested, as we have seen before. We have to handle conflicts. Here is an example of a non-serializable transaction are some of the things that we will see in engineering. And in this example, we can see an architect here and maybe a structural engineer here working on a flooring system, like the flooring system that you are being seated on. Now, the architect is trying to work on the floor, and the architect read locks the floor because he or she wants the floor wants to work on the flooring system, but they're only interested on the interior layout and not at the structural details. Now, the structural engineer is interested in doing this structural design on that floor, like they want to do, like put in the right reinforcement in the slab and things like that. So, the structural engineer requests a right lock on this particular floor. So, the structural engineer sends a message to the architect saying that I want a right lock. Now, the architect is notified of this particular event, and the architect may unlock the floor system, and immediately the structural engineer is notified that okay, now this thing is free for you. So, the structural engineer at this stage gets a right lock on the floor and goes about designing the slab, and this has no effect on the floor dimensions. However, after he or she finishes this, they update the flooring system by posting it onto the database. Now, the architect at this stage read locks the floor and goes ahead continuing with the interior design. Now, this process keeps going on. Note that here this is non-serializable because in a two-phase protocol, all the locks are attained in one phase and they are released in the second phase. Here we get the locks, release the locks, and get the locks, and we mix them and we mix all these locks as such. So, this kind of thing cannot be done using the traditional database management system framework. However, we can probably enforce this on the object databases, as we have done in our laboratory, where we have developed a collaborative transaction management systems. The other collaborative transaction management systems, which are developed at Columbia University, Brown University, and a host of other places, which incorporate some of the features that I have talked before, where we have lock management, deadlock management. We should have communication facilities, version management. Many database systems such as Object Store offers this version management, and we will soon see how it is done. Conflict management, because you can encode constraints in the object. As a result, you can have enforced conflict management. Now, I will briefly talk about some storage servers. So, in the architecture of the object oriented database system, I said there are four components: the query system, the object system, the transaction system, and the storage system. Just now I gave you a feel for how the transaction system should be, and now I will talk about the storage management and discuss how this is achieved in some of the commercial database systems. So, we can really divide the kind of storage servers that are available in the market into four types. The first type is called typeless page server. The second type is typeless object servers. The third one is tuple based object servers, and the fourth one is type based object servers. So, what is the difference between these four? I will come to this particular slide later on by explaining to you how things are done in a traditional database management system. If you look at the traditional DBMS, this is how the access is done. Suppose the application program requires a particular object or a table. I'm just mapping the tables and using the tables and objects here synonymously at this stage, because we are in the realm of object oriented databases. Now, the application program here requests a particular object. So, there is a buffer pool for the database management system. So, the application program looks into the buffer pool. If it is not there, it requests the server to give the particular object. So, because it's some kind of a structured ID exists, so from using the structured ID, I can go to the disk and get the appropriate page in here. So, I get the appropriate page in there, and from here the representation here is different than the representation which I use in the application program, and this particular object is now translated. The data structure of this object is translated into the data structure of the application program, and it is used by the application program. And after this is done, it is translated back into the buffer pool. So there is a translation process from the application program memory into the database management system buffer pool. And from here, I send it back to the server or disk storage. Now this is kind of little inefficient as such because there are a number of translations taking place. These particular slides are taken by an excellent book by Cattle, who discusses and compares a number of object-oriented systems. In object-oriented systems, we can take we take the object IDs, and the object IDs belong to a particular page, and they are directly swapped into the application memory, and by means of some pointer swizzling, we get the representation from the OID, that's the object identifier, into the application memory, and then we directly swap it back into the disk storage. What I've shown this example before when we talked about mapping the vehicle from the database to the application memory, and here I'm giving you a little more detail. And the way this is done, again coming back to this particular slide here, we can see that in the typeless page servers, what happens is that the page as a whole is taken into the application memory. The entire page is taken from the database into the application memory, and the application then operates on the objects. That means the methods associated with the objects cannot be executed at the server level, but the whole page is taken into the application memory, and then you manipulate on the objects, and there are methods associated with the objects which can be invoked at the client level. Examples of this are the Exodus system, which is a public domain system from University of Wisconsin-Madison, and we use that quite a lot in our work, and it's a very powerful system. Object Store is a commercial system which uses the same thing, and it's again we have used this in a number of applications, and I will describe Object Store later on. In the typeless object server, the unit of transfer, instead of being the page, it's the object. However, these things also have no notion of the class of the object or how to execute the object methods at the server level. The tuple-based object servers are extensions of the traditional relational database systems, except that they extend the relational database model with the object model. The type-based object servers are the most flexible of the lot, where you can type-based object servers where the objects at the server level can be manipulated, and you can manipulate them both at the server level and the client level. So these are very flexible. However, there is some overhead associated with them, so they tend to be a little slow for some of the applications. Here is an example of how Exodus goes about doing its work, and this is kind of a little tricky around here, where we create a unique object identifier, and associated with this unique object identifier we have a page ID, a slot ID, and a volume. The page ID tells you, the volume ID tells you where in the disk storage this one exists, the volume or the segment in the disk storage. The page ID will tell you what page it belongs to, and the slot ID will tell you the offset in this particular page where you can get. And there are two other numbers here, the unique and the offset, which are very little more complicated now to discuss through. However, this is to suppose this object is deleted, it makes sure that there are no duplicates, references to this object. So here we take the object ID and transfer it to the server through this process, where there is a unique user descriptor hash table, and this is mapped to this hash table. From there it mapped it into a unique user descriptor buffer pool, from there to the storage manager buffer pool to the disk storage. The actual process is a little more complex than this, but I have tried to simplify around here on the mapping from the OIDs from the application program to the server level. So this is a little detail which if you are interested in more information, you can get it from University of Wisconsin-Madison and talk to them directly on how you can get this. There's another package called the Orion. Orion is a research system which is developed at MCC, and the storage manager looks, and then now they have commercialized it as Itasca, and we'll talk about it a little bit later. And it has the storage manager there has several components like the access manager, object buffer manager, the storage manager, and the page buffer manager. So in case you need a particular object, the way you go about doing it is to call the storage manager. The storage manager first look into the object buffer manager, first call the object buffer manager to see whether it's in the object buffer pool. If it's not there, call the storage manager. The storage manager goes and calls the page buffer manager. So the page buffer is taken from the disk space and put it into the page buffer pool. From here, the access manager takes it and then puts the right objects in the object buffer pool. And here is an example of that process where in Orion, Orion is one of the systems which is a type based object server, and it uses some kind of a identity called the surrogate ID. Again, this is a fairly complex process, and this is called the typed surrogate. I'll try to explain that in a couple of minutes. The objects are not directly referenced in this case, but rather through in the object buffer pool we create something called a resident object table. The resident object table consists of a number of descriptors which are unique IDs here, 1, 2, 3, 4, which are again hashed into this. Now these UIDs point to these UIDs point to another data structure called an ROD. So this is the ROD here is called resident object descriptor. So the resident object table has got elements which point to this resident object descriptor, and this has the pointer to the actual object. This also has a pointer to the class object, and that's one of the reasons how that is one of the main reasons that in Itasca you can execute the methods in the class at the object level, because there is a reference around here. You can do it both on the server level and at the client level. And there are a number of things here to make it more efficient. You have the message cache, log cache, and you have a number of other flags and attributes attached to that, so that you know whether this particular object ROD points to a particular ROT, or if something has changed or some other application program has changed this object or not. So it keeps track of all these things, and this is a very complex structure here, and this complex structure makes it very flexible, but also it also makes it a little slow to run. Finally, to summarize, object oriented database systems extend object oriented programming languages by providing persistence, concurrency management, query management, and recovery facilities to object oriented programming languages. So you have programming languages such as C++, and there are R Smalltalk, R Lisp, and then associated with these programming languages you have a direct one-to-one map, that is the object oriented database systems, and these database systems, they help or extend the object oriented programming languages. So the typical applications for this object oriented databases are computer aided design, computer aided manufacturing, multimedia, hypermedia, operating system, groupware, office information systems, and so on. So what is the future for object oriented database systems? Well, the future is as follows. One of the things that you might see is, because of the investment made in relational databases, you might see an emergence of hybrid relational and object oriented systems. However, we may not take these hybrid systems should function as the best of the both, that is, the hybrid relational object database system should be as good, in the relational part should be as good as the most commercial relational database systems, and the object part should be as good as better than the commercial object oriented database systems, and let us see whether that will happen or not. Thank you, and I will see you in module 3.